I'm tempted to do more examples of finding Bezout coefficients, but I have a few examples written out in the lecture notes. So I will let you look at those and you should try some on your own. So maybe come up with some of your own examples. I want to do one more video on the Bezout's little theorem and show you how it's useful to prove different facts about number theory. For starters, let's prove, and again, both of these are in the lecture notes, but let's prove that this is called Euclid's lemma. So Euclid's lemma. Euclid was a Greek mathematician, lived approximately 2,300 years ago or so. So let's prove Euclid's lemma that if P is prime and if P divides a product AB, then P divides A or P divides B. This is a relatively intuitive fact, actually. The reason why I say it's intuitive is that we know that primes are the numbers that you can't split into smaller factors. So, for example, if you were to have, I'm just making something up here, but if you were to have something like 700, and you know that 7 divides 700, there's no way for part of, however you factor 700, it doesn't matter. It doesn't matter if it's 7 times 100, it doesn't matter if it's 70 times 10, or if it's maybe a little bit more interesting one, we could do 14 times 375. No, that's not a factorization. 14 times 50. There we go. I can math. 14 times 50. The point is that however you factor 700, a 7 has to go somewhere. You can't have part of a 7 go here and part of a 7 go there. Okay, because 7 is a prime. You can't factor it into smaller terms. This is not true for non-primes. So for example, 16 divides 32, but you can have part of 16 go into, you could factor 32 into, say, 4 times 8, and 16 does not divide 4, 16 does not divide 8. And what allows this is that you can factor 16 into smaller terms, right? It's composite, it has factors besides one in itself. So this is a fact about primes, and it's a pretty deep fact about primes. And if you have a prime that divides a product, then it has to divide either A or B. So what we're going to do is we're going to walk through the proof, and the proof is actually super tricky if you don't use Bezout's little theorem. If you have Bezout's little theorem at your disposal, that's like a tool that we have now. This is something that you can use to prove lots and lots of things. And this is, I think, a good example of one. So here's how the proof is going to work. Let's assume that P divides A times B. So assume P is prime and P divides A times B. Assume P does not divide A. Okay, so assume P does not divide A. In other words, assume A and P are relatively prime. Well, if A and P are relatively prime, that means that their greatest common divisor is 1. And therefore, by Bezout's little theorem, there exists Bezout coefficients. There exists values, say, x and y. By values, I mean integers, because we're still talking about number theory, but there exists integers x and y, so that 1 is equal to ax plus py, because it turns out that if a and p are relatively prime, then you can write 1 as a linear combination of a and p by Bezout's little theorem. And if we multiply both sides by b, this implies that b is equal to bax plus bpy. So here we've written b as bax plus bpy. And it's hard to see how that helps at first, except that we remember that we have an assumption that we didn't use. We're assuming that p divides a times b. So since p divides a times b, that means that just by the definition, there exists an integer k or whatever integer you want, but there exists an integer k such that a times b is equal to pk. And if we take this value if we take this term ab and replace the ab there, we get that b is equal to pkx plus bpy. So that tells you that b is p times kx plus by. In other words, p divides b. Okay, and so this proof is really aided by the fact that you can come up with these Bézier coefficients, and that turned out to be very crucial and very useful. You can take this one step further if you'd like. I'll leave this to you as an exercise. I leave it as an exercise in the book, but you can actually you can generalize this argument just a little bit, and I'll show you how. So suppose that A divides BC, and A and B are relatively prime, then A divides C. So you can adapt the previous argument to prove this, and I'll leave that to you as a sketch. One corollary of these facts, namely of the second proposition that I mentioned, is that it turns out when you're working with modular arithmetic, you can cancel in a certain sense. So we've already seen, I think it's worth just taking a step back here, we've already seen that if A is congruent to B and if C is congruent to D, then A plus or minus C is congruent to B plus or minus D. I'm being not great with writing it out, but I mean mod M, right, with some modulus. And likewise, AC is congruent to BD mod M with that same modulus. Okay, so there's a proposition where we talked about how congruences behave like equality signs for certain operations like addition, subtraction, and multiplication. Division is much harder though. But here's how division is going to play into this whole picture. It turns out that if AC is congruent to BC mod M, and if C and M are relatively prime, then you can cancel the C's. Then A is congruent to B mod M. And the proof is straightforward using the previous propositions. So the proof is straightforward. If AC is congruent to BC mod M, so if AC is congruent to BC mod M, then that implies that M divides AC minus BC. In other words, M divides C times A minus B. Since C and M are relatively prime, then from the previous proposition, it follows that. So it follows that M has to divide A minus B. And therefore, A is congruent to B mod M. Okay, this fact is false. If A and C are not relatively prime, I will let you come up with examples. You can think of, for example, C equals 0, but I will let you come up with other examples besides that. Okay, so this is again just a little key on how Bézier's little theorem is very useful for us in proving these number theory ideas.